So I wanted to talk about Gradescope. It's clearly a bit clunky. I had various levels of irritated emails at various points of time in the night, 2 a.m., 4 a.m., 6 a.m., direct messages on Slack. So I'm sorry for that. I will try to find a better way. But for now, it might be that some of you have been able to upload just one PDF, and you can select it for different questions. You can upload pictures of your cat or just blank pictures for the other questions. I know it's annoying, but for now, let's just do that and we will see how it works. We might even move entirely to Google Forms or something like that, where these options are better. I want to see how Connor and I feel in grading your answers this time, and then we will decide how if we need to switch or not. So for now, I apologize for the inconvenience. So Eric has a question regarding the problem last time, where we had the problem from the reaction, where we studied the work done when 50 gram of iron reacts with hydrogen chloride to produce something, something. So let me open up that problem once again. It said 50 gram of iron reacts with hydrochloric acid to produce aqueous FeCl2 and hydrogen. So it's an open, a big beaker. In this question, you can go into various levels of accuracy. The point to make here, the crucial point here is that you start with solid and liquid mixing together to form liquid and gas. Yes, you can try to be accurate here and try to take VI also into account in this problem. But if instead of that you did VF minus VI, the number would be so small. Think of it, you're producing hydrogen gas. It's just so much larger in volume compared to anything else you had. Now, the other question was, well, if my beaker is tiny and I produce hydrogen gas, won't it escape into the atmosphere? Of course it would, but that's why we assume that it's a big beaker and there is enough space for the hydrogen to come and stay here. The third thing, which is very interesting and which brings us to the topic that we will start from today, is why did we not use ideal gas equation for this px? Why did we keep dangling this px? Why did we not use the properties of the gas itself to calculate the pressure? And that's a very good point to start today's class. And it also connects to something that some of you, I think it was Deepika, who asked me in the office hours as to the notion of reversible change. So I introduced it last time. Let's go over it in detail today. So before we go into reversible change, let's recall for ourselves the concept of equilibrium. We introduced equilibrium very early on, and we talked about mechanical equilibrium and thermal equilibrium. The idea in mechanical equilibrium was if you have two things where the pressure is different, P1 is equal to P2. If P1 is more than P2, then at equilibrium, P1 equal to P2. If P1 less than P2, then also at equilibrium, P1 is equal to P2. So the thing about equilibrium is that both pressures become equal. If there is a difference in pressure, there will be mass transfer happening from side A to side B. So let's think of this concept in the context of, if I had hair, I would have said I was having a bad hair day. But clearly everything is being a bit clunky today. I think I have part of the reason. One moment. Okay. So let's imagine our beaker. And in this beaker, we had some system. This is the question. This is the system from last time. We had something happening at pressure P, and we had an external pressure Px that was the pressure of the atmosphere or something else. So let's imagine that we have this external pressure not imposed through the atmosphere, but imposed through some sort of a piston. There is a piston that is acting and applying a pressure external on this thing. And what we are trying to do here is to pull this piston upwards. We are gradually drawing it up so that the pressure of the gas decreases, okay? So this can be done in variety of ways, but we do know that for equilibrium to hold true, P external must be equal to P at all stages of expansion. For equilibrium to hold. So let's think of it another way. We have a gas. Let's say this gas is at 10 bar, and we want to decrease the pressure to 2 bars, right? There are two ways of doing it. So earlier, what did we have? We had the gas at 10 bars, and we had P external is equal to 10 bar, and everything was happy, right? P external was 10 bar, P gas was 10 bar, and there's nothing's happening. Pressure is equal. We are in mechanical equilibrium. Now we can do two things. One is to all of a sudden decrease the pressure of this piston from 10 bars to 2 bars, right? So we decrease the load that we had. How do we do that in practice? You can imagine that this piston is made up of, it's like a stack of weights in the gym, and you suddenly remove few of the weights from it instead of gradually reducing it. If you do that, the gas will come, it will come down to 2 bars. How will that happen? The gas will expand, right? If you decrease this pressure, the gas will also gradually start to expand, take up more volume, and the pressure will go down. This is, however, very different from the second type of process, where you gradually remove the weights at a time. You don't just decrease the pressure from 10 bars to 2 bars, you very, very gradually do it. If you do it in that way, then at any step of the process, P external will be equal to P, right? So it will look something like this. You had P and P external. You had P external, we started with P at 10 bar and P external at 10 bar, right? Now what we do is to change this P external to 9.99 bar, say, just for reference. This will also come down to 9.99 bar. Then we do it 9.98, and then this also comes down to 9.98, so on and so forth until we get to 2. The other way of doing it is to start at 10 and 10 and just immediately bring it down to 2. In this case also, it will be forced to come down to 2, but there is a key difference here. This one, you stayed at equilibrium all through, while in this one, you went out of equilibrium during this process. Gradually, you will come to terms with the fact that it's all new and you have to adjust and equilibrium will be restored. But during the process itself, you were not in equilibrium. And for those of you who like weightlifting or ever have been in a gym, you can imagine how this works like, right? You can think of the opposite step. You're carrying a stack of weights and someone immediately comes and puts 50 pounds on that stack of weights. You won't be very happy, right? You will get knocked down. You'll probably go out of equilibrium, irrespective of how strong you are. However, if someone gradually kept weight, you will be responding gradually. And this equilibrium is special because this change under equilibrium is special because at any step of the process, we have P is equal to Px. And what this means is if you stopped at this step and you change the Px to Px plus delta P, or you change the Px to Px minus delta P, the movement will immediately reverse in the opposite way. You can go back to what you were doing. So you can go along this process in either way. In this one, you cannot go in either way. The change is not reversible. You have really enforced a direction. You have gone from 10 to 2 in one way. If you go down the opposite way, the system will not look the same. You can do that. You can again go back and increase the pressure. But just like think of the weightlifting example, you were carrying 50 pounds, someone put up 50 pounds and took it off. Put it up again, took it off. It will probably cause a lot of skeletal damage, right? It won't look the same. Instead of that, you are gradually stacking weights, bringing them down, gradually stacking weight, bringing them down. You can change the system back and forth many, many times because you are always in equilibrium. So in the hydrogen chloride example that we did last time, we were not specified whether the change is done reversibly or not. We were not given that information. If we had been given that information, we could have set Px is equal to P and use the pressure of the gas to solve the problem. But we were not given that. So all we had to use was there is an external pressure, and it magically canceled out, not magically, but it canceled out of the derivative expression. So our life was fine. Okay, so I'm going to focus on this. Most of the problems that we do in physical chemistry will be reversible change. Typically, it will be specified explicitly what is the nature of change. Sometimes there will be problems where you will have to think about irreversible change, but this is the type of problem when it's in an exam or it's in homework, and if it's not clear as it happens, you're always welcome to come and clarify on Slack. So let's see what this means. So we are talking about reversible change where P is equal to P external at each stage of change. The change could be expansion, the change could be compression, it could be something else. So in this case, our dW, d with a cut because it's not an exact differential, which was minus Px dV. Oh, something else. My screen share stopped, right? Yeah, it froze again. Sorry about that. So if dW is equal to minus Px dV, which we had in general, then if we were doing reversible change, then this can be written as minus P dV, where P is the pressure of the system. So I'm really emphasizing a simple point again and again, which means here we had pressure of surroundings, which were driving the change. Because remember, first law of thermodynamics, we talked about work done by surroundings on the system. So it's always the pressure of the surrounding. But under equilibrium, Px is equal to P. Why, Teresa, your cat is really profound. 67777, why, it's a deep thinking cat. Cool. Pakoda might, there were some demands for Pakoda showing up during the class. He might. Okay, so now what we can do is to calculate W by doing an integral of this thing. And here we can say, let's say we are going from some V initial to V final, and then we will have PdV. This P, now we can use from equation of states that we know exist in PChem. We can use those equation of state to calculate, to put in the value of pressure over here and do this calculation in a nice way. Earlier, we were at the mercy of knowing what is the external pressure. Now we don't. So let's remove that page. Okay. So we can actually calculate this integral, and let's see how it looks like for an example. So in practice, how does it look like? Let's say we have a perfect gas or an ideal gas. So we have PV is equal to nRT valid. And let's say this gas is expanding from volume VI to VF. So how does it look like? Let's draw a PV diagram. So in the course of next few classes, you will be drawing a lot of PV diagrams or PT diagrams or VT diagrams, things like that. So we have some volume VI and we have some volume VF, and the system is going from this volume VI over here. Let me first, yeah, this volume VI over here to this volume VF over here. We haven't yet talked about pressure, so it could be anywhere along here. We will get to that in a moment. So let's say the initial pressure is PI. Let's say this is where we started at initial pressure PI. Then we know it is expanding. So the final pressure for an ideal gas, once it comes to equilibrium, must be lower, right? So the final pressure must lie over here, PF. So we know it's going to start from this one, and we know it's going to end here. We need to now calculate the work done, which is given by dW is equal to minus P external dV. So what is P external dV? If we assume case one that each stage, that the expansion is reversible. Case one, we assume that expansion is reversible. In this case, P external will be equal to P of the gas, and that itself is nRT by V by using the ideal gas equation. Therefore, dW is equal to minus nRT dV by V, and now we can calculate W is equal to minus integral nRT dV by V, going from VI to VF is equal to minus nRT ln natural log of VF by VI. We get a closed expression. We can actually calculate this integral. How would this look like in the pressure volume curve? Temperature, this is done at a constant. So we are doing an isothermal expansion. I should have stated that very clearly. It's an isothermal expansion. Temperature is constant and we are not changing N also. The number of moles is same. Remember in the iron chloride example, the number of gas molecules was also changing, so it was a bit different. Here, if you try to plot the path taken during expansion, reversible expansion, that will be given by pressure is equal to a constant number, nRT for our case, divided by volume. X, Y is equal to constant. That's the curve we are hoping to plot. And there was one of the modules where I went into this into a lot of detail, and you can see how it looks like. If X, Y is equal to constant, then what can we say about Y? Y is constant by X, right? So if X is equal to 0, Y tends to infinity. Similarly, if Y is equal to 0, X tends to infinity, and it looks something like this, right? So we can draw that curve over here. I think the name for this in coordinate geometry is hyperbola. If maybe I'm wrong, if I'm wrong, please correct me. So this is the curve given by PV is equal to nRT. And the thing that we just calculated, minus nRT ln VF by VI, is nothing but the volume under this curve. Sorry, the area under this curve. That's what we calculated. So that is the work. Now let's take another moment to think about it. It's the system that expanded. When a gas expands, you get work out of it. So in this case, you can see VF more than VI. So I'm doing a bit of sanity check to see it makes sense. You should always do sanity check in PChem or otherwise. Therefore, ln VF by VI must be positive. Therefore, W is negative. Does that make sense? It does. W positive would have meant that you did work on the system. The internal energy of the system went up. In this case, the gas expanded. When gases expand, you can extract work out of this process and do something with it. So that's what you got. You were able to extract, we were able to extract plus nRT ln Vf by Vi energy through work. We could put this to some use. We could drive an engine through it. We could drive a chemical reaction, or anything you want out of this. So this was case one. Let's look at the case two, when this process was not reversible. Let's say the expansion is irreversible and is done very quickly. What does it mean? We had the gas at pressure Pi. So that was the piston that I showed you last time, which was at a high pressure. And you immediately decrease it to a pressure PF. Why do I say decrease? Because you can see here that PF is smaller than Pi, right? So if you immediately decrease it to PF, in that case, the W will be given by minus integral again of minus Px dV. But now Px is not given by P. Now the Px is actually given by Pf. And I want you, if this is not obvious, I'm going to star, draw a dog around here so that you really remember. Pakora wants you to think about this carefully. That's my drawing of Pakora. It's terrible, I know. When it was reversible, we were able to do Px is equal to nRT by V, assuming ideal gas. If it was van der Waals gas, we would have used a separate expression. Now we cannot do that. Now our Px is directly the Pf. The integral can still be calculated because Pf is a constant, right? So in this case, it becomes minus Pf, and the limits of the integral are minus Vi to Vf. So that is simply minus Pf, Vf minus Vi. So let's call this case one as color blue. And let's call this case two as color red. Let's go and plot this color red in this PV diagram. How will that look like? That's going to be this area, right? That's the area of the rectangle. PF multiplied by VF minus VI. If you do a sanity check, you can again see it's negative. So something interesting happened. Do you see what happened? The work that you can get out of the system, if the change was happening reversibly, is higher than the work that you can get out of the system if the change was happening irreversibly. This is super interesting. This is profound, and this deeply connects to the second law of thermodynamics, which we'll visit later. So what we saw here through this example is it is not possible to obtain more work out of a system than that for a reversible process. Here I showed it to you through an example, through this gas expansion. This is, however, very generically true, very true in general for, or if we can restate it in another form, we can restate it as the maximum work available from a system. And I just showed you for a mechanical gas expansion, but this can be very general, chemical, mechanical, anything. operating between. So what we have done here is to fix the initial point and the final point, right? So we know that initially it's always going to be Pi Vi, and finally it's always going to be Pf Vf. So given these two things, operating between specified initial and final states is obtained when the change places reversibly or under equilibrium. So this is really connecting to, this is our first glimpse of the second law of thermodynamics when it comes up later. And this is a beautiful, simple, and a profound statement. And you can relate to it even from day-to-day experiences. Anytime your workload explodes, you are taking 2 classes, next semester you decide to register for 6 classes, you won't be as productive. It's not going to happen, right? It's a good idea to gradually increase your workload. I like running. Last semester, I never really ran more than 20 miles in a week. And last semester, I was like, okay, let's try to run 70 miles a week. Bad idea. I got a stress fracture and I was screwed up for a long time. So you want to increase your workload gradually. You want to increase it in such a way that whatever change is happening in the system, anytime you decrease the workload, the change happens in the opposite direction. If you're out of equilibrium, it's not going to happen that way. And we will revisit this in second law of thermodynamics. So now we are in a good spot to write down our first law of thermodynamics in a general way. I already did it last time, but I will write it again. So du is equal to dq plus dw coming from expansion plus dw others. We mostly looked at dw expansion, but there can be other sorts of work too. Any questions about this part? No question, you're all silent. You're still recovering from homework 1.
The DW, is that expansion?
Yeah, EXP is expansion. Okay, so okay, there's some Zoom check.
Sorry, would you mind showing one more time the PV diagram for the second process? Or did we actually draw that? I was just looking at.
Oh, sorry. I didn't really draw one because that looks like this.
Oh, okay. Okay, thank you. Just
no, that's important. That's a subtle point. So good. So now we can talk about change in U. So we talked a lot about how does W look like, right? We saw how to calculate it. It's slightly deceptive because if you have taken Gen Chem, you must have thought about work done on a system and everything. And now we started looking at it from a slightly more abstract perspective. We try to really keep in mind that dW is always pressure of the external system, pressure of the surroundings multiplied by change in volume. It's only under reversible change that this pressure of the surroundings becomes the same. This is only true for reversible change. If it's not reversible change, you have to use the external pressure, whatever it was. So we talked about dW. We will talk about dQ when we get to entropy, but I want to start to talk a little bit about du and see what does it mean to change the internal energy of the system. To do so, we have to introduce the concept of heat capacity. So what I'm getting with here is to think about changes in U. For example, I am interested in calculating things such as partial U, and now we are going to get heavy into Calc 3 land. So get ready. Partial U by partial V at constant T. Can anyone tell me how much would this be for an ideal gas and why? So I want you to think about it, and I just saw a question on Slack. So Matt asks, why did we set P external is equal to PF in the work integral for the non-equilibrium case? So in this case, what we did that we were starting here. We were starting at this point over here, right? Everything was happy. The system was happy. The surroundings were happy. We were at initial pressure PI, and my screen froze, sorry. And maybe I'll start using the cable next time because the screen froze is annoying for me. It must be annoying for you all too. How many times does it happen in real life that you're talking to someone and they just freeze and they stop talking and you go like, I think you froze. And you smack them once and they start talking again. It's just the virtual world peculiarities. So we are talking about this point over here, right? We started at this initial pressure PI. The system was at PI, the surroundings were at PI. The reason why we set P external is equal to PF, because in order for this change to happen, the piston was suddenly changed from PI to PF. You had a piston that was at PI, and what you did was to suddenly lift this piston and reduce the pressure to PF. And that's when you allowed the change to happen. The change happens after this point, once you did this. That's why P external has been set to PF. It's a subtle point, but it's a good question. Yeah, so Abby replied, just a guess, if V changes, then P will change to compensate. So overall use stays the same. It's even simpler. Anyone wants to try again? What is partial U by partial V at constant T for an ideal gas? Have we talked about U as a function of T for an ideal gas? It depends only on temperature, precisely. This is number of degrees of freedom multiplied by RT by 2. So there is no volume dependence. So for an ideal gas, this is going to be 0. In general, though, it is not going to be equal to 0. And we want to understand how does it look like. And we will see why does it matter. Those are the things we are going to calculate. Yeah, thanks. So in order to do that, we have to introduce the concept of heat capacity, which I briefly alluded to in the past. Now we will be a bit more formal about it. Heat capacity, denoted by the letter C, typically, measures, as the name says, the capacity for heat. What does that mean? Someone said it's kT by 2, not RT by 2. That depends on your unit of measurement. If you're looking per atom, it's not exactly the same thing. It's just unit. If you're looking per mole, it should be R. If you're looking per atom, it should be K, right? Are you counting number of atoms of the gas, or are you counting number of moles of the gas? So C measures the ratio of heat absorbed by a system, heat Q, absorbed by a system to the amount of temperature change. So if you change the temperature of a system by a certain amount, let's say 1 Kelvin, how much heat will you have to give to the system for that change to happen? This change, so roughly it is partial amount of change in delta Q, amount of change in Q divided by amount of change in temperature. That's what we are looking at. You gave a certain Q, amount of heat delta Q, and that caused the temperature to change by delta T. And that's heat capacity. And as some of you might recall, water has one of the highest heat capacity known of all materials. So in India, I grew up around Bombay for a while, which is right on the sea. And Bombay is well known for not having a lot of temperature change. Why? Because it is on the sea. So what happens on the sea is that whatever heat that comes up into the system, if the heat capacity is very high, it takes a lot of heat to change the temperature very slightly. So when India starts to get very, very hot, all the heat goes into the water and the temperature increases just ever so slightly. It also means the winters are relatively less brutal, because even the temperature, even though the heat has been sucked out of the atmosphere, most of it just goes to cool the water only ever so slightly. So we will formalize this notion. Of course, we know that heat, you must have seen this in Gen Chem, but now with your superior knowledge of Calc 3 and exact differentials and partial derivatives and things like that, will we be marking, if someone asks more with number of moles or number of atoms, that's really up to you. For different problems, it will be defined differently. Don't worry about it too much. So we know that heat is a path functional. The change in heat of a system really depends on how the change was carried out. So we could have heat capacity at constant volume. That would be given as change in Q by change in T at constant volume. And we will show in a moment. So this is tricky, right? You should be a bit upset over here, like, how can you really write that? Q is not an exact differential. What does it mean to do that? What we will show is that, oh yeah, that's annoying. So we had this dq by dt. In reality, we should write it as something like this, right? It's because it's not an exact differential. We have to, sorry, we should write it as d cut q by dt. That's a better way of writing it, right? So actually, let's be consistent there. What we have is a change in Q that depends on the path taken. And here I'm telling you that that change happens at constant volume. So what we are going to show next is that this heat capacity is the same as the change in internal energy of the system with temperature at constant volume. And this is for any material, any gas. It doesn't have to be ideal or things like that. Similarly, we can define a heat capacity at constant pressure, which will be given by what if this change happened by keeping the pressure of the system constant. So we write down P here as constant. That will lead us to the concept of enthalpy, and we are going to get that in the coming lectures. But for now, we are going to focus on this one. Let's try to understand what does it mean. So we are making a statement here that, and it's a bold statement. We are saying that the change in heat, the amount of heat required to drive a system to change its temperature by a small amount, delta T, in general will be depend on the path taken. Even though I wrote it's at a constant volume, there can be many paths that you can take at constant volume, right? It can be done in a variety of ways. But here I am showing you that it actually is the derivative of a simple state function, the derivative of u with respect to temperature at constant volume. So let's see why this is the case. In order to see this, we can write down our favorite theorem, the first law of thermodynamics, which says that du is equal to dq plus dw, right? Or du is equal to dq minus p dv. We are going to ignore other sorts of work. So what are we trying to find out? We are trying to find out heat capacity at constant volume. What does constant volume means? This means dv is equal to 0, right? That's the definition of constant volume. Therefore, du is equal to dq at constant volume. Therefore, and now we are talking about constant volume. So when we divide by temperature, we have to switch to partial derivatives. Therefore, partial u by partial t at constant volume is going to be dq by dt at constant volume. So, and this is our definition of heat capacity at constant volume. This integral is kind of ill-defined. This derivative is kind of ill-defined because we have a path function. We don't know how to differentiate it. But here we have something. This one was clumsy, and this one is nice, as you will see. For example, let's go to our ideal gas. There we saw that equipartition holds true. What does equipartition means? Equipartition means that U is equal to number of atoms, let's say in this number of degrees of freedom, multiplied by RT, right? So now we can say, let's say we have a system with n point size atoms. So it's not a molecule, these are atoms and they are all point sized. In this case, NDOF is going to be 3n, right? In the first homework, in the second homework set, in the first problem in the second homework set, you will be calculating this number of degree of freedom for a few gases, think through it, and that will give you some more intuition. So this is equal to 3n, therefore U is equal to 3n by 2 RT. So now we can calculate the heat capacity. For an ideal gas, we can do something concrete. Heat capacity is equal to partial U by partial T at constant V. There is no volume over here. Life is very, very simple. 3n R by 2. So this is the thing that I mentioned earlier in the class, if you recall, that the heat capacity for an ideal gas is going to look like this. It will be constant. People had found out in the early 20th century or even much before that this is not true. This is actually really wrong. It starts to be true only at very high temperatures. At low temperatures, the heat capacity goes to 0, and at very high temperatures, it becomes constant. This is the reality. So this shows that basically equipartition, which was our starting point, this formula kind of starts to break down. This U is equal to NDOF by 2 multiplied by RT breaks down at low temperatures. And why does that break down? That breaks down because in order to derive equipartition, we assumed that energies are quadratic in nature. What do I mean by that? We assume that the kinetic energy is, for example, given by half mv square. You see a quadratic term here, half mv square. It will apply also if the potential energy is given by half kx squared, things like that. But what happens at low temperatures is that things are no longer quadratic. Quantum mechanics starts to hold true. And this breaks down. And so it really needed quantum mechanics to explain this. Why is this heat capacity so important? It looks like an alien concept. Sure, I used it to tell you that this helps me understand why doesn't Bombay get so much warmer, or any place on the ocean. It doesn't have to be in India, even I would say California, but California has more issues going on in temperature, so I won't go there. But in general, heat capacity matters because it's something we can measure directly. If you want to study, for those of you who are biochemistry majors, for example, one of the best ways to understand the nature of interaction that is happening inside a given biomolecule is to heat it and see how much heat did you have to put into the system in order for the temperature to go up by a slight amount. And once you do that, let's say you measure this in experiment, right? Let's say you perform an experiment and you measure the heat capacity as a function of temperature. You know through your superior knowledge of thermodynamics gained through PChem 1 or Chem 481 that his heat capacity is a partial derivative of the internal energy with respect to temperature. So this curve is telling you something about how does the internal energy change with respect to temperature if the volume is kept constant. So you can back calculate from this curve and develop a model for the internal energy. You can see how should the internal energy depend on the function, right? And that's super important because by doing a bulk experiment where you're pumping heat into the system and seeing how much heat does it take for the temperature to go up, you can go back and come up with a model for what is the nature of interaction. For example, is it hydrogen bonding? Is it van der Waals interaction? Some of them will follow, they will all follow different types of U terms. You know, if it's van der Waals, the good model for U for a van der Waals is different from the U for a hydrogen bonding term. So you can go and gain information about the molecular scale interactions by looking at this heat capacity as a function of temperature. So it's super important. It can be measured, for example, through something called a bomb calorimeter. It's a pretty simple instrument which you can use to measure the heat capacity. And there are lots of fancy instruments too. So Devin asked if in both of these scenarios, are we to assume that there is no work being done by the on or by the gas? Yes, the work is only expansion work, and we have said that it's a constant volume process. If it's a constant volume process, dW is 0, and life is simple. What does it say in the graph next to the blue curve? Which one? Over here? Here it says breaks down at low temperature. Here it says bomb calorimeter, which can be used to get things experimentally. And this one is reality. This one is constant. So in reality, in reality, the heat capacity goes to 0 at low temperature, which you can see it does not happen for an ideal gas. So it's a good time to stop here. I want to just mention what we will start with in next class. So next class, what we are going to do is to look more closely at the nature of U. So we know that U can be expressed as a function of PVTN, right? We will focus on U as a function of PV for a fixed composition system and try to play with it a little bit and see what type of expressions, useful expressions that we can develop through this. So what is the purpose of playing with all these partial derivatives? The purpose is to develop expressions that have terms that can be measured in experiments. For example, here, partial U by partial T at constant P is heat capacity, which can be directly measured in the experiment. So we want to connect our molecular level understanding to something that is directly tangible in experiments. So that's what we will be doing. And did I have anything else to say? Oh yeah, so I want you to read a little bit before next class on something. I want you to go and refresh state functions and make a list of which ones have we studied so far, and just remind yourself which are the state functions, which are the path functions. I also want you to think about extensive and intensive properties. What does it mean? Which ones are extensive? Which ones are intensive? I want you to think about these things: P, V, T, Q, U, CV. Which of these are extensive and intensive? I would like you to think about this. Okay, so I will see you in next class. Thank you very much.